interpretation. So I'll be talking about the work I did for my PhD at the University of Leeds, which was using synthetic aperture radar backscatter data. So these type of images that I've got in the back here to monitor volcanic eruptions. So remote sensing data is very useful for volcano monitoring, as it can provide continuous and frequent information about an eruption, especially when ground-based measurements are limited or too dangerous to collect. So the idea of the project was to look at the potential of various backscatter methods to examine different types of volcanic deposits. So in comparison to other data sets, SAR backscatter data is less frequently used still. So here I've got optical image showing La Soufrière volcano on St. Vincent. With optical imagery, it's possible to get a direct view of the ground surface and look at how it changes through time, and they're relatively simple to understand when you look at them. However, they are limited by the time of day, as well as being dependent on cloud coverage. So this can limit the observations you can make, especially at tropical volcanoes, where there's a lot of cloud coverage and during ongoing explosive eruptions. So cloud coverage. Over the last few decades, synthetic aperture radar methods have become more frequent for volcano monitoring. Most commonly used is the radar phase component, which can be used to observe ground deformation. However, for this, the ground surface needs to remain stable between acquisitions, and therefore in areas where you have high vegetation coverage, and when you have volcanic material that's deposited or removed, we lose coherence and this data set becomes a bit more limited. The counterpart of synthetic aperture data is the amplitude. So this is what I'm looking at. So this is a backscatter image. And it is less frequently used, mainly due to the ambiguity in the data interpretation side of this data. However, it can provide a snapshot of the ground surface at that particular point in time, and therefore can potentially provide additional information when other data sets cannot. So when I'm talking about radar backscatter, it can be broken down into this equation here, which is for a single pixel in a SAR image. Luckily for us, most of these variables here are known and provided by the satellite. So this includes satellite parameters, the antenna gain, and the range. We're interested in this factor here, which is the backscatter coefficient. And this represents this surface scattering of the scattering properties. Represents the reflectivity of the ground surface, basically, and is controlled by various parameters, including some satellite parameters, such as polarization, wavelength, and incidence angle. These will remain the same for a single track or sensor. However, it is also affected by the scattering properties of the ground surface. So these are the gradient of the slope. So if you have a slope that is facing towards the satellite, it'll appear brighter than one that is facing away. The surface roughness. So this is on the wavelength of the satellite. So a smoother surface, more of the energy is directed away from the satellite, so you get a lower radar backscatter signal for these, and a rougher surface will appear brighter. And lastly, the dielectric properties, which are most commonly referred to indicate the moisture content of the ground surface. So a drier surface will have a lower radar backscatter than a wetter one. Yes. So so the main aims that I'm hoping to bring across through this presentation are looking at what volcanic deposits we can detect using radar backscatter in either one type of eruption, if you can look at different processes for similar eruption, or looking at very different styles of eruptions as well. How we can clear up these signals by applying different methods and corrections, and as well as trying to extract quantitative information that would be useful for monitoring ongoing eruptions. So I'm going to do this by showing you 3 different case studies of 3 very different types of eruptions. So the first one is the explosive eruption at Volcán de Fuego in Guatemala in 2010. The second one will be the 2010 to 2013 effusive eruptions at Pu'u crater in Hawaii. And the last one is the 2021 dome growth at the Soufrière St. Vincent. All right, so starting off, I'm going to talk about the explosive eruption at Fuego in 2018. So this was a uncharacteristically large eruption for the volcano, with multiple pyroclastic flows that affected a lot of the drainage systems around the volcano, as well as caused the deaths of several hundreds of people in a community at the base of the volcano. It had widespread ashfall, as well as multiple periods of high lahar activity in the months following the eruption. So using high resolution SAR data, we try to observe the different volcanic deposits present, and that were just in place during the eruption, as well as trying to link patterns that we saw within these backscatter signals to specific processes on the ground surface. So for this case study, we used 4 different methods, and I'll go into detail about explain these in more detail as I go through. The top 2 ones, so using single images and change difference images, are 2 commonly used methods applied to SAR backscatter data in volcano monitoring. So if we look at this type of data first, so this is a single SAR backscatter image before the 2018 eruption at Fuego, and this is one after the eruption. And you can see this decrease in radar backscatter here, which is associated with the emplacement of the pyroclastic flow. So commonly, you can use this type of data to look at changes in the backscatter data just by comparing 2 images, but you can also take the ratio of 2 images, such as this, which helps highlight where things are changing. And for easier visual interpretation, you can put this into an RGB image and produce these kind of images where you can see decreases in radar backscatter as blue and increases in red. So this helps just with the visualization of where the changes are happening. So we did this for the Fuego data set, so for both the ascending and the descending track, and we could see 6 drainages that were affected by the 2018 pyroclastic flows. Overall, it was a decrease in the radar backscatter, probably associated with smoothing of the ground surface by some of these finer deposits. However, we did see more complex patterns. So these are examples from further down in some of these drainage systems. So in this case up here, this is related to where a drainage system has been partially infilled, and it produces this stripe-like pattern in the radar backscatter, which is associated with the slope that is facing towards the satellite is actually increasing in radar backscatter, and the one that is facing, sorry, I got that wrong way around. The one that's facing away from the satellite is showing an increase, and the one that's facing towards the satellite a decrease. So you get this very distinct stripe pattern where a flow has completely infilled and overtopped the drainage system. We get more complex patterns. So this is an example of that, where the flow actually has completely overtopped and the associated changes in the radar backscatter that we see here strongly depend on the pre-eruptive land coverage. So depending on whether the deposit has been emplaced on a field or removed vegetation, you'll get a different signal. So it is quite important to have an understanding of the pre-eruption land coverage to be able to interpret what these signals actually mean. So if we zoom in though into one of these areas here, it looks something like this, and you can see it's actually quite difficult to see where the edge of this flow is. So to try and improve this, we looked at just a single pixel time series. So this is for this area here, and we can see when the pyroclastic flow is in place, we have a drop in the radar backscatter. We can apply a simple linear least square inversion to this to try and to calculate this change in radar backscatter associated with this drop here. To do this, we use one image after the eruption and 2 images before, and we can produce something that looks like this, which is already slightly clearer to see differences in between the flow and the surrounding area. And we can add more images into this step estimation. So this is it with 5 images and then with 15. So it's clearing up the image a bit better. And if we apply this to our whole scene, we get something that looks like this. So it's similar to these, to the RGB images I showed earlier. However, you can see that the boundary of the pyroclastic flow is much sharper now. The more complex pattern where the flow is overtopped as well is much sharper, so you can better correlate this with information from the ground, as well as more subtle features or subtle changes in the backscatter. So some of these minor pyroclastic flows in some of the other drainage systems come out clearer in this, as well as some of the internal structures that we actually can see in the pyroclastic flows. In addition to being able to see some of these changes in the pyroclastic flow, by producing these longer time series maps, we saw this more subtle feature as well on the southern flank, where you can just about see seems to be a slight decrease in the radar backscatter, which we think is associated with some of the ash fallout that occurred during the initial eruption. While we found that using these maps, so the RGB maps and these step estimation maps, were useful for visualizing the emplacement of the pyroclastic flow, we found that at Fuego, at least, they weren't well suited for visualizing lahar activity, as the lahars produce much lower magnitude changes in the SAR backscatter than the pyroclastic flows did. So to kind of try and see these processes in a bit more detail, we produced these backscatter grids, which would allow us to observe the temporal trend across a whole data set. They are a bit confusing to look at first, so I will break it down using a simple cartoon first. So if we have 4 points in time, we can look at the difference in radar backscatter between each possible pair. So between the first two, the ground remains completely the same. So the corresponding grid square in the grid for this would be 0. Between 2 and 3, we have got some in place deposit, which causes a decrease in the radar backscatter. So that square would be a decrease then. Between 3 and 4, the surface has increased due to changes in the surface roughness. So we can say there's an increase there. So we can fill out our grid for all possible combinations. and until the whole grid is filled. So if we do this for a specific area in our data set, we get a grid that looks like this. So this is for the upper section of the main pyroclastic flow associated with this eruption. We can see this period of low, relatively small changes in the radar backscatter, which is associated with a time before the eruption where there was low volcanic activity as well. And then we get this sudden decrease in the backscatter, which is associated with the emplacement of the first pyroclastic flow. And then we get quite a lot of different points in this data set where the backscatter changes either magnitude, quite suddenly changes in magnitude, or actually completely changes in signal direction. So by identifying these points of interest in multiple grids along the pyroclastic flow, as well as comparing it to rainfall data, local rainfall data, we can say we're able to identify potential periods of high lahar activity. So if we say these lahars, and if we compare this to ground-based data, so this timeline here shows you the reported lahars in the data during this period of time. The second one just shows you the same data, but in the same time intervals as the SAR acquisitions. And the third one here is just, this one shows periods of time that we identified that had lahar activity. So generally we were able to capture quite a lot of these periods of high lahar activity. Some of the ones that we completely missed, such as these ones in September, we think these are because the lahars were quite small and potentially either didn't reach far enough down the drainage system, so cover multiple grids, or were too small in magnitude to actually be observed. So at Fuego, we found that the explosive deposits we could map out the different explosive deposits here. The high magnitude changes in radar backscatter, so the ones associated with the pyroclastic flow, were relatively easy to visualize across all methods. However, these extended time series helped us identify more subtle features such as the ashfall, potential ashfall, and actually possible periods of high lahar activity. In contrast to the explosive eruption at Fuego, which was characterized by sudden changes in the radar backscatter, we wanted to look at an effusive eruption as well, which would allow us to look at more long-term changes in the backscatter. So to do this, we used the 2010 to 2013 lava flows at Kīlauea crater on Hawaii. So this eruption was characterized by 3 lava flows and multiple inflation and collapse events at Kīlauea crater itself. So for this data set, we had a much larger SAR data set. And our main aims were to try and map out the emplacement of the lava flows and possibly characterize the backscatter signals associated with the changes after the emplacement, as well as quantify the inflation and collapses at Kīlauea crater. So we started off by kind of trying to do the same thing as we did at Fuego, which was looking at pixel time series. However, we came across this very interesting pattern in the data set. So this top plot here shows you time series for an area in the radar backscatter over some vegetation, which should have remained completely stable. But we see this very repetitive signal in the backscatter data, which correlates very nicely to which of the 4 Cosmos SkyMed satellites actually acquired the image. So it seems that it seems like there's a satellite dependency in the backscatter data. So to correct for this, we did a principal component analysis. So this here is our first principal component. It makes up about 75% of the variation in our data set and looks very similar to the satellite dependency that we see. So before I show you how it looks like after we apply the correction, so this is a single pixel time series over the lava flow and one over vegetation. So this is before any correction. We can see that the time series are very noisy. If we remove this first principal component from our data set and replot those pixels, we can now see the emplacement of the lava flow is much clearer, and even you can see the recovery afterwards, as well as now the pixel over the vegetation is stable, as we'd expect it to be. So if we look at this corrected data set that we have, we can calculate the time of emplacement. So when the radar backscatter changes suddenly in the data set, this can either be a sudden drop in backscatter or a sudden increase, but this depends on what the underlying material was before the lava flow was emplaced. Doing this, we can produce maps like this, which shows you the timing of the emplacement of the lava flow. We can plot it in time intervals like this, which helps visualize the progression of the flow through time, where the flow front is active, and when it changes directions, as well as how active the flow is. And the final flow maps that we actually produce just from the SAR backscatter data match well with maps produced by the Hawaiian Volcano Observatory at the time of the eruption, as well as maps produced through other methods. So this one here is using the coherence data. Yes. So while these lava flows were being placed, Pu'u crater, where at the top here, was showing periods of inflation and collapses. So we wanted to look at some of these as well. So this is Pu'u crater in a backscatter image. This dark feature in the middle is an active lava lake. And due to the side-looking nature of the SAR sensor, due to the side-looking nature of the sensor, slopes that are steep slopes facing away from the satellite that have a gradient steeper than the incidence angle produce a radar shadow. So these are areas where we can't collect any data, where the satellite can't see. Respectively on the other side, so if you have a slope that is facing towards the satellite and has a gradient steeper than the incident angle, you produce a radar layover. And this is what this is showing here. So this is Pu'u crater. You got a radar shadow and the radar layover. So you can use the width of the radar shadow to calculate a relative height for the feature casting it. So we did this for Pu'u crater to calculate the depth of the crater floor. So this is a method that has been applied elsewhere. So it's been used at lava lakes for Nyiragongo as well as Dualeh. So it's not a new method. However, the Hawaii data set, because it's a very dense data set, as well as has extensive ground-based monitoring, allowed us to actually examine the limitations and the assumptions that go into this method in the hopes that to understand it better and then be able to apply it elsewhere. So if we zoom into this section where most of the inflations and collapses happen, we then plot multiple different cross sections across the crater itself. We get these different plots. So each of them, you still can see the inflation and collapses associated with each of the eruptions. However, you can see that the magnitude and the errors on some of these are much bigger. So if we look at, for example, this first dark green plot, which correlates to this cross section here, we can see that the cross section comes in at a very oblique angle to the radar shadow. So it makes it quite difficult to pinpoint where the shadow starts and ends, which then produces these large error bars, as well as the shadow itself here is actually, because of this oblique angle to the satellite look direction, isn't being cast into the deepest part of the crater, but rather alongside the crater, onto the crater wall. So you're not actually imaging the deepest parts. Similarly, with this light green cross section here, you also get this plateau feature in the data set. And this is actually due to the interaction between the radar shadow and the radar layover from the other side of the crater. And when you get the interaction between these two features, you underestimate the actual depth of the crater. So until the crater floor has risen to a certain level, all the data points will cluster around like this. If we compare the measurements that we have to the actual heights calculated by the Hawaiian Volcano Observatory at the time, we can see that for the black cross section, which we are confident was the best one we could get for this crater, we capture the Komomo fissure eruption height relatively well. However, for the second collapse in August 2011, there's still quite a big difference. So the main reason for this difference is due to the geometry of the collapse and the geometry of the crater itself. So the first collapse was relatively uniform and happened at once, whereas the second one occurred over a longer period of time, over in steps, and it produced these terrace-like features. So the shadows that were actually produced in the radar data were being cast onto individual terraces rather than into the main bit of the crater. So not possible to visualize the complete depth there. So there was quite a lot of things that we were testing at Hawaii dataset, but I'll leave it with these two. The mapping of the initial emplacement of the lava flows worked relatively well using SAR backscatter data, and the radar shadow method works well, depending heavily on the geometry of the SAR, the geometry of the SAR sensor, as well as the geometry of the feature you're looking at. So these are important to consider when applying this method. So this brings me on to the last case study that we looked at. So this was looking at the 3.5 months of dome growth at La Soufrière St. Vincent in 2021. So there was dome growing there for a couple of months before the eruption transitioned from effusive to explosive. So we wanted to look at the SAR data and see whether we could quantify this dome growth through time. So initially, we tried to apply this radar shadow method because the dome itself grows into the shadow of the crater wall. However, due to the geometry of the dome, the shadow itself, shadow from the crater wall doesn't interact with the highest point of the dome. So we couldn't quantify the true height and therefore volume of the dome through time. We tried doing this then through another different method. So this is now based on the assumption that the local incidence angle, so the local incidence angle is the main scattering property of the SAR image, at least over the new 2021 dome, and that the surface roughness and the dielectric properties are uniform across this through space and time. Based on this assumption, we can say that the backscatter data there is proportional to the gradient of the slope. So I've got here two TerraSAR-X images, one from January 2020 with the new dome here, and one from March 2021, where the new dome is much bigger. And these are the cross-section lines for these two images. So you can see here, you've got the radar shadow from the crater wall, and these are the profiles for the new 2021 dome. So based on the assumption that the backscatter is proportional to the gradient, we can integrate across these range lines to calculate the relative height, relative heights. We have to correct for the gaps in the data due to the radar shadows, but we can do this using the width of the shadow to get a relative height change, and we get these profiles that look something like this. We can see generally they match up quite well to the pre-eruptive profile, except here, of course, where this is the new 2021 dome for January and March. So we can do this integration for each range line that crosses over the dome, and we get plots that look like this. So these are showing you the topography that we've retrieved from the SAR data, and the second line of plots just shows you the difference between the retrieved height that we have from the SAR data and the pre-eruptive DEM. So for the two high resolution images, so I've got here TerraSAR-X and Cosmos SkyMed, we can see that the 2021 dome generally is imaged relatively well. We do have areas where there are differences between the retrieved topography from the SAR data and the pre-eruptive DEM. This is even clear. You can see this a lot more in the Sentinel, which is a lower resolution satellite. These distortions are related mainly to mainly related to radar layovers, actually. So while we can correct for changes, for the no information over the radar shadow, the radar layovers still produce a signal in the backscatter data, and this signal ends up distorting our profiles. So to try and mitigate for some of these lines with a lot of error, as well as this, the striping nature of that we get because we do this line for each range line, we apply a triangular mesh interpolation. So each triangle has multiple points in it from different range lines. So this helps with smoothing across the range lines, as well as bridging over gaps. Plots. So this is the dome for those three images again, and using these we can calculate dome volumes and extrusion rate. So we get a plot like this. So the different color points here represent the different sensors. So we had 5 tracks that covered this point from 3 different sensors, Sentinel, TerraSX, and Cosmo. For the time from December until March 2021, we had a relatively low extrusion rate of about 2 meters cubed per second. If we zoom in onto the last 2 weeks before the eruption transition from effusive dome growing to an explosive eruption, we can see that we actually have an acceleration in the extrusion rate. So this is about 18 meters cubed per second. And this change in the extrusion rate that we see and calculate from the backscatter data actually correlates with changes in SO2 measurements that were measured, as well as there was some visual observations that the extrusion rate was changed in the couple of days prior to the eruption, as well as the change in seismicity. So it's quite so it was quite neat that we were able to image and capture this change in the just from the backscatter data itself. So we were able to observe the changes in the extrusion rate, as well as increase the frequency of the number of observations that were made of the dome through time, as well as just quantifying the changes that we were able to see in the single backscatter images. So I'm going to kind of try bringing stuff together and wrapping up for this bit now. So it is an exciting time for SAR in volcano monitoring. There are a lot of satellites currently acquiring data and imaging, which means that there's a lot of data out there, and it's also becoming more accessible for volcano monitoring purposes. With this, that means there's a lot of different ranges in the viewing geometries, so you can look at a deposit in different from different directions, which sometimes helps understand how the ground is actually changing through time. Some of these second generation satellites now from Cosmo, and I think RadarSat 1 as well, and now will have dual polarization capabilities. So this is something I didn't talk about at all, but there's a lot you can do with polarization data sets for volcano monitoring, as well as missions like InSAR, which will have multiple with different wavelengths. We've got quite a lot of we have quite a range of wavelengths that could be applied to volcanic settings, which would be interesting to see how the deposits vary in these. So from what I've looked at, I was able to look at a lot of high resolution data, which is very useful to actually look at changes in the eruptions and looking at a lot of small variations. However, some of the lower resolution satellites, such as Sentinel, were able to capture changes, especially when they were larger magnitude. Having high temporal resolution really helps with monitoring volcanoes, because you then can see individual or smaller changes over time, which is helpful. I mentioned briefly having different viewing geometries, so having ascending and descending can be helpful to look at deposits either on different sides of the volcano, depending on the steepness of the volcano, but also to try and mitigate distortions introduced by the satellite viewing geometry. And it was possible to look at quite a range. It's possible to look at quite a range of volcanic deposits using SAR data. So while large changes in backscatter, large topographic changes and surface changes are easy to observe in the radar backscatter, we found that it is possible to distinguish between also more widespread and subtle changes, especially if you apply, have additional information about the eruption style, the pre-eruptive land coverage, and other data sets that can complement the backscatter data. It really helps when you're trying to interpret the complex signal in this data set. Further, the backscatter data can tell us more than just where the deposit's being placed. The complexity within the signal can tell us about the various processes within the deposit, as well as how the ground is changing over time. And having frequent and multiple data sets can provide useful information from multiple different viewing geometries, which can really help and be important in volcano when observing an ongoing eruption. So thank you for listening to me. I would be happy to take any questions.
Thanks, Edna, that was great. So please pose questions in the chat or the question and answer box, and we can work through those. I have a question, Edna. So in terms of relevance for disaster response, and I guess you kind of touched on this, how easy would it be to automate some of the types of analysis that you presented, for persistent monitoring during eruption? Or does it require a lot of site-specific and data-specific sort of expert interpretation?
So it ranges. So for some of the very simple methods, so just looking at, 2 images, that can be automated quite easily. Even for example, for the pyroclastic flows, doing these extended time series where you look at a step can be done relatively fast. Some of the other ones, so looking at like the dome growth one, that one at the moment, it's probably initially hard to set up. So it's probably you have to set it up for for a specific geometry or a volcano. But once it's set up, so for example, for St. Vincent, I can run that quite fast and get measurements from that. So it depends at the moment a bit on the type of eruption and what you want to do, but it is possible.
Great. Chi, do we have any questions from the live audience?
I have loads of questions, probably very basic. Yeah, this is all very new to me and I find it really interesting. But if you have questions, would you like to go first? Okay.
I've got a question. Hopefully you can hear me okay from the back of them. So the backscatter grid that you did, you had like different locations on the pyroclastic flow. It was like A, B, and C. And it looked like the backscatter grid from B was majority red, which was a increase or decrease, I can't remember, an increase in backscatter, and the one from A was majority blue. Yeah, exactly. I was wondering what the reason was for B being more red compared to the others.
So I think the answer for that is that, so pyroclastic flow, like the change associated with the pyroclastic flow, is not necessarily uniform across it. Sorry, a lahar is not uniform across. So in some places you'll have material being removed and other places deposited. So I think some of these changes will reflect into that as well. Yeah. Also so it's this one here, which I chose on the edge of the pyroclastic flow. So maybe as well, it's not capturing, the full extent of where lahar would be going, but rather just a section. So if more material is being deposited in that kind of area, that could explain as well why there's kind of the different signals between the different grids.
Okay, great, thanks.
Okay, like very basic questions. First of all, the backscatter data, is it the same as the intensity data that we also talk about, or is it two different data sets? Oh. Slide.
Sorry, I can't.
Okay, great. You're back online. So my question was, is the backscatter data the same as intensity data, or is it different? Oh no, frozen. Are you frozen? Okay, you're not. Okay, great. Backscatter data, is it intensity?
Yes, in very simple terms, yes. There is this calibration factor for it, but simply speaking, there's a lot of different terminology used for backscatter.
Okay,
Makes
cool.
it a bit annoying and confusing.
Thanks. And then, like, when you receive the backscatter data or the SAR imagery, are they already geo-referenced? Because I was wondering, you're trying to use the width of the shadow to calculate the crater depth, and then does that rely on proper georeferencing? And then if it's always changing, then the DM is always changing, and then like maybe you have already touched on that, but I didn't fully understand.
Yeah, so maybe I didn't explain it well. No, so backscatter images, so you produce them directly from the raw data as well. So initially they will be in radar geometry and not referenced to a DEM at all. So for the radar shadow kind of method, you just, because you know the size of the pixel in the radar geometry, you can measure it from that, and it's a relative height change as well. So it's a height for a feature, but you don't have a reference to what that is in the real world, kind of thing. So you can look at the changes in height for each image, and you can get then the changes through time, and then you would have to apply that to either tie it down with some ground-based measurements or DEM, but then that would depend on the quality of the data you can get.
Thanks, Edna. We've got some questions in the chat now, so we'll start with Michael. So, hi Edna, great talk. Would it have been possible to map pyroclastic flows and lahars emanating from La Soufrière during its explosive phase?
Yeah, so we had a look at some of those images as well. So you could see for the La Soufrière eruption, there was actually also a lot of ash signal that you could see in the backscatter data, as well as the pyroclastic flows. So it's tricky in some senses to differentiate between kind of where the pyroclastic flow and the ash kind of, they overlapped quite a lot in that sense. I think there was some work being done on looking at the backscatter data for the status for that eruption for the pyroclastic flows. I think it captured most of the pyroclastic flows, but some of the smaller ones, it missed those. Yeah.
Great. So we have another question. So from David Sheen. Hi, David. Thanks for a great talk, Edna. How does seasonal snow affect the different methods you showed today?
So yeah, I didn't look at any ice cap volcanoes or snow ones, but it would affect. So you would get different signals when there is snow or seasonal snow. So also there's some studies that have looked at how ash being deposited on glaciers produce different signals than on the bare rock. So I think you could still apply quite a few of, especially some of the visualization maps to the situation, but you would have to keep in mind, how ice would interact and how the moisture, differences would also change the signal.
Great. Another question from David Sandwell. So did you look at InSAR coherence to get an outline of the lava flow?
So I did have a look at the coherence. So let me go back to that slide. So this map here is produced. So this is the lava flow map that I produced from just from the coherence data. So when the lava flow is in place, you lose the coherence. So I produced that purely from the coherence data, and this one for the backscattered purely from the backscatter data. So they're completely separate. However, you could do something where you could combine them, or kind of where one works well, or where one doesn't work well, see if the other one could infill that data, kind of thing.
Perfect. A question from Bonnie Pickard. So what software do you use to conduct the analysis, e.g. ArcGIS for the change detection in backscatter?
So I used, so for processing the SAR data itself, I use Gamma, which is commonly used, I think, for processing InSAR data and backscatter. And then for the kind of further processing of so the RGB images and producing some of these maps, I used either QGIS or MATLAB to do this.
Great. And there's another question from Fatia. It's quite a lot, so there's a few questions actually. So if you can read that out of the Q&A box, that would be useful.
Yeah. One second, I need to find. Okay. So thank you for the inspiring presentation. I'm quite lost on how you determined the area which increased, unchanged, and decreased in the Fuego case study. Okay, so I'll start with that. So kind of, I assume you mean with this plot kind of thing. So the areas so it's the difference between, well, I'll go back to the RGB ones rather. This is, so the areas, so what I'm doing here is by just looking at the two images. So if you take the difference between the two areas that have, so if an area has decreased between 1 and 2, it will have reduced in the radar backscatter, and this just shows you, kind of visualizes it as a blue area. So it's just visualizing the change between the two images in a sense, and looking at the so it's doing that. And so at that point, it's just changes in the signal between the two images themselves, and then you would have to go and actually interpret what that pattern or shape would what that correlates to on the ground. And then I hope that answers the question, sorry. So what software did you utilize to process the data? So for these ones, I was using to make maps. Initially, I was using both MATLAB, but also QGIS to make the maps. I haven't worked with Snap, so I'm not sure whether this is an adequate enough. The question was, is Snap adequate enough to process the image? Which I'm not sure. Sorry. Sorry, it's a long question.
I think that's the next bit. You said you use MATLAB.
Yeah.
But maybe the last bit, how to incorporate different band data sets.
So for these kind of these RGB maps and step images maps, I didn't work on, so I always worked on individual kind of data sets. Because of the different viewing geometries, it's quite difficult to incorporate them together. However, why I was doing so, I was kind of processing them in parallel and then comparing kind of my observations and interpretations between the two data sets. Yeah.
Great. So there's another one coming from Sam Mitchinson saying, hey, how does water impact the SAR data? e.g., could one use SAR to measure changing water levels in crater lakes?
Wonder. So yeah, so you can see water quite well in SAR data. So just an example, this here in La Soufrière in the crater, this is a small crater lake. So you can actually see, you can calculate the area at least, how the area of the lake changes over time. So yeah, you could probably do that. To what extent? Yeah.
Great. So question about the recordings. Yes, the recordings will be made available. So if you Google COMET Webinars, we'll make it available next week. And then one more question from Mohammed. So very interesting research. Do you think different radar wavelength bands have an effect on monitoring pyroclastic flow?
Yeah, I think they definitely, it makes a difference. Not only for the pyroclastic flows, actually for the lava flows as well. So I had a quick look at that, and the signal you get is quite different, because the wavelength plays a big role in actually determining how the surface roughness of the image is, how the surface roughness affects how the backscatter signal. So having different wavelengths would be sensitive to this change. So it would be interesting. You could probably do a comparison if you had multiple wavelengths over a single pyroclastic flow. If you could use, you would probably see differences in the signal associated with different material size, depending on how the range and material size you have. So that could tell you maybe something about, yeah, the material that you're looking at and the roughness.
Cool. So I think that's it for questions, and we're coming up to 5 o'clock, so we can call it there. So thank you again, Edna, that was great. Thank you for everyone that's attending. So one last minute question, which speckle filter did you use?
So I did this a while back. I did a comparison between different speckle filters. I think I ended up using the one that was, I think it was the gamma map one, which is, can't remember the reference off the top of my head, but if you're interested, you can write to me.
Get in touch with Edna. Great, so thank you. We'll see you in the new year. So our next webinar will be in January. Chi will email out details as usual when we have a date confirmed. So thanks again, everyone. Enjoy the rest of your day.
Thank you, Edna, for a great